Okay, so this is the last lecture for Math 383, complex analysis. I do not believe we will be mentioning either of the two. Oh no, we will be mentioning one of them. So we'll have to wait till the end of the lecture to get a final count as to which of the two dueling mathematicians has the most references, because at least one of them will be getting at least one reference today. All right, so what I want to do today is I want to start off by talking about a inequality, the Cauchy-Schwarz inequality. Talk a little bit about Fourier transforms and talk about applications, in particular the uncertainty principle in mathematics. I actually went and talked to a physicist earlier this week as to how does he view the uncertainty principle, and he actually gave me, well, he views it as a mathematical statement, okay? So I've mentioned this article by Wigner before. If you have not read it, strongly encourage you to do so, The Unreasonable Effectiveness of Mathematics. It is just so phenomenal how many different things can be described by mathematics. And even better, how many different diverse systems can be described by the same mathematics. So once you learn how to do one bit of mathematics, you can actually apply that in many different settings. Do a search and replace for mass and charge, with a 1/r squared classical force, and you have a tremendous amount going on there. Okay, so how many people have not seen the Cauchy-Schwarz inequality? Does that count as a second mention? It does count as a second mention. All right. Is there anybody who has not seen this inequality? Okay, so this is one of the standard ones in real analysis. Extremely useful. It basically says if I have two objects u and v, then the dot product of u and v in magnitude squared is less than equal to the square of the magnitude of u times the square of the magnitude of v. Or if I take square roots, basically the length of u dot v is less than equal to the length of u times the length of v. All right. There's lots of different ways of proving this. So the book goes through, Wikipedia goes through and does one of the standard proofs using the discriminant. I'm going to give a slightly different one. What is the most useful inequality in all of mathematics? Nope. Almost. You have to be a little bit more specific. Sorry? X squared greater than 0. A little bit more. So anything, if I square anything, it's greater than or equal to 0. X is real, right? So use x squared greater than or equal to 0 if x is real. This is an exceptionally useful inequality. A lot of things come down to the fact that if you have a real number and you square it, it can't be negative. And so one way to prove the inequality is to look at the magnitude squared of something. So we'll consider maybe the real case. So we'll do the real case. We can look at u plus lambda v. And so what do we know about the length of u plus lambda v? Greater than or equal to 0, right? And this is u plus lambda v dotted with u plus lambda v. So we get 0 is less than or equal to the length of u squared from u dot u plus 2 lambda u dot v plus the length of v squared. Right? And the v is neat lambdas, thank you. So now I have a quadratic in lambda. I can put in any lambda that I want. And my goal is to get to the u dot v is less than or equal to the length of u times the length of v. So because this is a quadratic in lambda, I can ask where is the smallest, right? And so I will leave this as an exercise to try to finish the proof of this. Find lambda that minimizes. And again, it's going to be pretty similar to the argument that was given up here by looking at the discriminant. It shouldn't be too surprising that it's going to be a very similar argument. It comes down to we have a quadratic, and we're concerned about where is the minimum value or where are the roots of this quadratic. It's governed by the discriminant. You can prove the Cauchy-Schwarz inequality by just divinely inspired choice of lambda, right? If I just happen to say, let me put in a specific choice of lambda, and I'm going to get this. When you look at this, you might try to figure out what would be a good choice of lambda to get to have everything to work out and come out correctly. So I will leave that as an exercise to you to finish the details of this argument. Just continuing, we're going to be getting into quantum mechanics soon, and in quantum mechanics, we're going to have operators that do not commute. And that makes the mathematics a lot more interesting. And it gives us the possibility of seeing relationships that we wouldn't have otherwise. So a lot of you know I love Rubik's Cubes. With Rubik's Cubes, it's a highly non-commutative group, which allows you to have cycles of moves that can do wonderful things to pieces. If you've never seen this before, the Baker-Campbell-Halster formula is absolutely wonderful. If I have a matrix e to the x and another matrix e to the y, well, that's going to be matrix e to the z. Let's say everything is a square matrix. But z is not going to just be x plus y. If we have real numbers, e to the x, e to the y is e to the x plus y. But when we see e to the x, what is e to the x actually? It is a power series. It's a power series in the matrix x. And you can show that when you look at the powers of x, they're not going to grow that rapidly. The coefficients will not grow that rapidly. So when you divide by the factorials, you will get the sum converges, and e to the x will make sense for any value, for any matrix, square matrix you put in. And there's formulas that actually tell us, if you want to write that as e to the z, what does z look like? And you have a wonderful expansion in terms of what's called commutator. So the commutator of two quantities, x and y, measures how close they are to commuting. So if they commute, the commutator is 0. So the commutator of x and y is just xy minus yx is 0 if they commute. So we're not going to be using this formula in what we do, but it's not surprising that we have a formula like this, because if the matrices x and y commute, everything from this point onward vanishes. If I now have my power series, I can just move the matrices freely through each other. And then e to the x, e to the y can become e to the x. So they should, z should be x plus y in the case when they commute. And then the question becomes, if they don't commute, what is it going to look like? Okay. So, I grabbed this from Wikipedia. I actually thought, since it's the uncertainty principle, having it in another language and blurry would be a nice way to start. So you can see lots of different variations of how you want to phrase it. It's even better on the blown up screen here, because it's even worse than it is looking on my screen. Can anybody read what that font means over here? I know we were having some discussion about trying to figure out symbols before the start of class. What is that quantity? I'm sorry? You sure? Could it be h bar? Because there's a 2 pi dot, right? The resolution is not good enough for me to tell whether or not there's a bar going through it, but because there's a 2 pi down below, I'm pretty sure. So h bar is the reduced Planck's constant. H bar is h divided by 2 pi. So I would never have h divided by 4 pi squared. So that's almost surely an h up there. P and Q are related to the position and the momentum operators. P for position, Q for momentum. And the more common way, for those who are laughing, the worst notation I ever saw in a physics book was P equals MF. Anybody want to guess what P equals MF was? Yes, P stood for force, M stood for mass, they got that one right, and F was acceleration. Does it matter what letters you use? No. But boy, can you confuse people. The more common way of phrasing it is the uncertainty in your location in X times the uncertainty in your evaluation of the momentum is at least a certain number, that you cannot resolve position and momentum arbitrarily well simultaneously. And if you think about how you try to do an observation, let's say you wanted to know how far away the moon was from us and how fast the moon is traveling. What might you do? I'm sorry? Well, how would you figure out how far away the moon is and how fast it's traveling? Yes, send a laser to the moon. Now, what happens when that laser hits the moon? Bounces back, but it does give a little bit of a push to the moon. Are we really worried about disturbing the moon? No. The push from that little bit of laser is not good. But when you're doing things on the subatomic scale and you're trying to localize where something is, all of a sudden now the active measurement can do a tremendous amount of damage to where it actually was. And so in terms of trying to figure out precisely where something is and how fast it's traveling, the active measuring is going to disturb the system. And so we cannot simultaneously measure the position and the momentum to arbitrary precision. This tells us that there is a fundamental limit to how well we can go. How would you completely destroy quantum mechanics? So what do we do to make quantum mechanics go away? Yes, that h bar to be 0. So if h bar was 0, then quantum mechanics vanishes and it all becomes classical. You no longer have things quantized. You no longer have this uncertainty principle. And so this is a deviation from classical mechanics. And you can often look at things and expanding in terms of powers of h and looking at things like that. There are other versions of the uncertainty principle. I think you might see energy and time. Is that one that you often see? So yeah, there's lots of different things. Okay. I am taking these from notes that I used when I was an undergraduate at Yale. These are the notes I sent to you. So because these are the notes that I am using, I am going to adopt the notation they used there. So what is different from what we've done before? There is no 2 pi. So does anybody know what rationalized MKS units are? How fast is the speed of light in rationalized MKS? 1. What is the gravitational constant? 1. So you adjust as many of the constants as you can to be 1. You choose the units appropriately. When we talked about Kepler's law and the orbits of planets, did we talk about that briefly in this class? We're looking at logarithms. Yeah. We measured the distance of planets from the sun in terms of astronomical units and the period, the time in years. You can choose the units you want to use. When I do physics, I actually do not like to use the rationalized MKS units because I can't look at the equations anymore and see the physics. The physics is all good. I actually like to see the little CT, speed light for time, to actually see this is the time axis. And this is how the speed of light is coming into play. Does it really make much of a difference, though, if we have a 2 pi or if we don't have a 2 pi? No. So sometimes we jokingly talk about rationalized MPS systems for mathematics. And in that, 2 pi equals 1, e equals 1, square root of 2 equals, it's correct up to standard factors like that. And just when you're doing arguments like this, you just have to be a little bit careful that you might make some small mistakes like this, but you'll eventually mostly have things correct. All right, so again, not a big deal that we don't have the 2 pi. And so I want to just go through a bunch of exercises. These are all pretty standard. The Fourier transform of the derivative. So if g is the derivative of f, and the Fourier transform of g hat is I c f hat of c. Does this give you a justification for why we dropped the 2 pi?
Yeah, because otherwise you get a 2 pi.
Right. Otherwise, you get a 2 pi there. So, there's no such thing as a free lunch. If you want this formula to look nice, sure, you can do that, but you have to pay a price in another form. And so it's, how do you want to simplify things as much as possible? And by doing this choice of the Fourier transform, it then makes differentiation and multiplication very nice. We do have a factor of I. Well, that's not horrible. That is reminding us what's going on. We're not going to be able to get rid of I. But we can get rid of the 2 pi's. All right, so let's prove this. And all proofs today will be physics proofs. Okay? So that means To make it a rigorous mathematical proof, you just have to go through and say, what conditions must I assume about my functions so that all the steps I'm doing can be justified. So typically, if you assume the function has some level of differentiability and some level of decay, then you're going to be okay. Maybe I need my function to be square integrable, maybe whatever. But you put in enough conditions so that everything can be justified. So G is the derivative of F. So let's look at G hat of C, which is going to be the Fourier transform of G of X e to the minus I xc dx, which is the integral from minus infinity to infinity of f prime of x e to the minus I xc dx. I think we've done this before. How should we handle this integral? Integrate by parts. We have an integral of f prime. So when you see that, another Pavlovian response, okay, I want to be thinking integration by parts because I've got the f prime. And if I integrate that by parts, that's going to become an f. So I'll let u equal e to the minus I xc, and dv will be f prime of x dx. This way, v is going to just be f of x, and du is going to be minus I c e to the minus I xc. And so now g hat of c is going to be uv at minus infinity infinity minus the integral from minus infinity to infinity of v du. We assume we have enough decay so that the boundary term cancels. So assume decay so it vanishes. And again, that's not a big deal to assume that we have enough decay so that the boundary term vanishes. And now we have the minus reinforces. We'll get an I C integral from minus infinity to infinity of f of x e to the negative 2. So distinct. Make that a fancy I, e to the negative I x c dx, which is I c f hat. So this is just the standard proof that the Fourier transform converts differentiation to multiplication. And of course, if we were then to do the Fourier transform again, what should the Fourier transform of multiplication become? What would you guess? So if the Fourier transform of differentiation becomes multiplication, would you think maybe Fourier transform of multiplication becomes maybe differentiation? Not necessarily, because we have these factors of I coming into play. So if your function is even, the Fourier transform of the Fourier transform is the original function. Other times you sometimes have to do it 4 times before you get back to the stuff. So the Fourier transform of multiplication, if h of x is x f of x, then the derivative of f hat of c is just minus I. So let's just prove this as well. So we want to take the derivative with respect to c of f hat of c, which is the derivative with respect to c of the integral from minus infinity to infinity of f of x e to the negative I x c dx. And I actually got the exponent right. What do I do? Yep. And what does waving my hands allow me to do? Yep, which can I do? Switch things, yes. And so that's now the same as the integral from minus infinity to infinity of d by dc f of x e to the negative I x c dx. Well, f doesn't have any c dependence, so we get f of x times negative I x e to the minus I x c dx. We get minus I x. I'm sorry, I can't bring out the x. So we get minus I integral from minus infinity to infinity of x, f of x, e to the minus I x c dx. And this is what we were calling our function h. So this is minus I h hat of x. And so that is the desired proof. So that if h of x is x times f of x as multiplication, then the Fourier transform of h is going to basically be the derivative. Again, I've got a minus I over here. I can put it over on the other side and make it an I over here. So there's this really beautiful interplay between derivatives and multiplication. We saw an application of this in solving differential equations. By taking Fourier transforms, rather than having derivative operators, we now have multiplying by polynomials. And multiplying by polynomials is much easier to work with than derivatives. More standard identities we need to do. So we need to deal with translation. So let's say I have some function f, and look at a new function, g of x is f of x minus a. So one of the other reasons I like this lecture is it's a great opportunity to talk about the standard things we do in math. When I have an operator, I want to see what happens as I change my inputs a little bit. As I make changes on the input, how does that change things on the output? Well, we saw when we were doing probability and the central limit theorem, I can rescale things. And so how does the Fourier transform behave under such rescalings? All right. So we want to calculate g hat of c. So g hat of c is the integral from minus infinity to infinity of g of x e to the minus I x c dx. But g of x is just f of x minus a, e to the negative I x c dx. Okay, I want to convert this to something involving the Fourier transform of f. So how could I change this so this will look like a Fourier transform of f? Change variables. What variable change should I do? Okay, so if x minus a equals y, then x equals y plus a, and dx is just dy. So this then becomes the integral from minus infinity to infinity of f of y e to the negative I, and then x is y plus a. So y plus a c dy. Well, I can pull out an e to the minus I a c, I have an integral from minus infinity to infinity of f of y e to the minus I y c dy, which is e to the minus I a c f hat of c. And so, again, very nice transformations between a function g, which is just f translated by a, and the Fourier transform. Okay, then the next thing you could do is what's the Fourier transform under scaling? So essentially, this is changing how fast your time is moving. So if I want to calculate h hat of c, again, all these calculations are essentially the same. So you go from minus infinity to infinity of h of x e to the minus I x c dx. So minus infinity to infinity f of rho x e to the minus I x c dx. What change of variables do I want to do now? Yeah. So rho x equals t. So x equals t over rho. Thus, dx is dt over rho. So this becomes the integral from minus infinity to infinity of f of t e to the minus I, and then x is going to become t over rho. So it'll be t c divided by rho. And then dx is dt over rho. To get 1 over rho, integral from minus infinity to infinity of f of t e to the negative I t c over rho dt. What does that integral equal? sorry. Yeah, so what will it equal? Yeah, it's f at c over rho. If you want, just put in your mind parentheses over there. We are just doing the Fourier transform evaluated at c over rho. So the Fourier transform of a function, if I rescale it by a translation or by dilation, the resulting Fourier transform behaves very nicely. Okay. And so this is, of course, the definition that I am used to using. The two-pi. Right. And so I had copied this before. And I went down to this page to paste it in. And it pasted like that. The reason is I had pasted it just like that and just shifted things over and added some blank space. So when I copied it, it only copied the outer box. It didn't copy the inner box I could put inside. Right. Now we are back to the notation that the book is using, but we no longer have the two pi's. Okay. And so this is a really nice problem. The Fourier transform of a Gaussian is a Gaussian. And we've done this calculation before. The book has done this. It does it a nice way by looking at it through differential equations and making some arguments like that. It does start off with the assumption that you know that the integral of the standard normal is something related to that you know how to do that calculation, which is often done in multivariable calculus by doing a really strange thing of taking a one-dimensional integral and squaring it, making it a two-dimensional integral, and using the polar trick of replacing dx dy with r dr d theta. This is a natural thing to do because we have an integrand that only depends on your distance from your origin. So whenever you see something like that, you should be thinking of your polar coordinates, spherical coordinates, something like that. So I'm not going to bother proving this one. We've actually done this already. Urge you to do this, urge you to look at the attempt to do this using differential equations. The Gaussian will come up a little bit later, so it's just good to record right now that with this notation, if f of x is either the negative x squared over 2 divided by square root of 2 pi, then f hat of c is either the negative c squared over 2. And again, you can see that the pain here is these factors of 2 pi. And the reason we have the pain is because we made multiplication differentiation nice. There's no 2 pi's there. And so we're paying the cost in the formulas over here. Okay. So now we're ready to turn to the main part of the lecture. So imagine we have some function f, which is an L2. What does it mean for a function to be an L2? It means the integral of the absolute value squared is finite. So you can actually think about this as a probability distribution. And so I was listening to a YouTube video this morning by Peter Shore on his discovery of his algorithm. And he starts off by talking about some comments Feynman was making about trying to come up with negative probabilities. And what he was saying is you can have negative probabilities, but whenever you are talking about an observable quantity, all the probabilities must sum to something that's non-negative. So there can be negative probabilities, potentially, it just can never be observed. And so over here, we will use the absolute value of f squared as our probability distribution. And so we are assuming it's integrable, so we might typically normalize it to just have integral 1. As long as the integral is finite, you can always adjust it to have integral 1, so that's not really a big deal. So when you're trying to look at theorems, you often want to ask, what is the appropriate normalization? In terms of what should this product be? Well, if I rescale my functions, I could make things a lot smaller or a lot larger. So to some extent, we always standardize this. If I have something that's not 0, what's a good choice for its value? Frequently, you can rescale to make it 1. The only thing that you can't rescale to make 1 is something that's actually 0. Because then no matter what you multiply it by, you've actually seen this in differential trigonometry. What is the derivative? Well, no, let's look it up. What is the sine of 45 degrees? Okay, the sine of 60. What is the derivative of sine? So we've gone back and forth between using degrees and radians. The derivative of sine is cosine, the derivative of cosine is minus sine, only if you're using radians. If you're using degrees, there's a factor of pi over 3, I'm sorry, of 2 pi over 360. And this is one of the reasons why we like to use radians, because if you use radians, the arc of a circle is the same as the angular measurement, on a unit circle. And that's the power of radians. It gives you the limit as h goes to 0 of sine of h over h is 1. Well, because the limit is not 0, I can adjust that limit to be anything I want. And we use radians because now we've adjusted it so that it has a limit of 1. That's very similar to what we're doing here. This is something you've seen before, but maybe not emphasized. We might as well adjust this integral to be 1 and have it as a probability distribution. So adjust so that the integral of minus infinity to infinity of the absolute value of f of x squared dx equals 1. And then for the next part, we're going to just look at a bunch of standard objects that we've studied before, the expected value and the variance. So the expected value of something is just x times the probability density, and you integrate over the whole space. The variance is going to be the value x minus the mean, minus what its expected value is, square that, and then times the probability distribution. So we can calculate E and V for a nice density F, for a nice probability distribution. We can then play the same game in the Fourier transform space. And we have C, we have F hat of C. So let's calculate the expected value. So it would be C times the absolute value of F hat squared. And similarly for the variance. Notice that we have these factors of 1 over 2 pi. If we're trying to show that something has to be at least a certain size, having the 2 pi's or not is really not going to make much of a difference. It's going to just change what that quantity is. The presence of the 2 pi's here is because of how we're defining things. It's really not that fundamental. What matters is that if you look at the product of the variance v, coming from the function f, and the variance coming from the function f hat, that product has to be at least a certain size. Another way of saying that is, imagine you have a Gaussian with smaller and smaller variance, becoming more and more peaked. The Fourier transform, we actually calculate up, it's e to the negative x squared over 2. So here we have done things where it is the same, it's just one distribution. We do this calculation now where you have f of x not being the standard normal, but a normal with, say, standard deviation sigma. And what you'll see is you'll have an e to the negative x squared over 2 sigma squared down below. You'll have an e to the negative sigma squared c up above. That it's going to become more spread out. And this is related to what we did a moment ago. If we rescale things with a rho, then on the other side it becomes 1 over rho. And so what's going on is that if we take a Gaussian that's sharper and sharper and sharper and more concentrated, the limit of sigma is going to 0, then on the other side it's going to look like a Gaussian with larger and larger variance. So that the more one is localized, the less the other is. And the idea is that what works for the Gaussian actually works in general. That the more precisely how tight f is, the less you know about f hat, the more spread out f hat is, and of course vice versa. All right. So the mathematical statement is that if we adjust so that the L2 norm of f equals 1, so think of absolute value of f squared as a probability distribution, then the product of the variances, v and v hat, is at least 1/4. If I didn't adjust f to have L2 norm 1, well, what I could do is just multiply f by 1 over 10, 1 over 100, 1 over 1,000, 1 over a million, and it will decrease both v and v hat. So I could make it arbitrarily small. So there has to be a condition such as the absolute value of f equals 1. So whenever you're doing problems, you always want to ask, how do you want to normalize it? I know some of you have worked with me on projects involving L functions, and you can normalize in several ways. You can have the L2 norm of the L function equals 1, or you could have the first coefficient be 1. And different normalizations are valuable for different things. And so here, the key idea is that we need some kind of normalization. The natural one is to choose it as a probability distribution, so the L2 norm equals 1. Okay. So now we're going to introduce a couple of operators. So we have the Q operator and the P operator. So Q is multiplying by X, and P is essentially taking the derivative. This is a 1 over I, it doesn't really matter. What is the physics that's lurking in the background? Yeah, these are the position and momentum operators. And this is why we're using the letters Q and P in the physics if you got any of those, the position and momentum operators. The fact that this mathematics describes physics is absolutely amazing. Right now, we are just doing a statement on pure mathematics. We're just looking at, I want to multiply by X, I want to take the derivative, I'm going to look at what happens. And so the first statement is PQ minus QP. Well, that's the commutator. Yes. So position operator in physics is basically giving you where the particle is, where the object is at a given moment in time. Is that the fair description? You want some way of getting your hand on these quantities associated to objects. And again, it's been a long time since I've done quantum, so I wanted to make sure as many physicists were here as possible today, because it's been a while. We can't talk about absolute position or absolute momentum. We would love to have like a Dirac delta spike, that the particle is precisely at this location and not some kind of smoothed out probability distribution. And you have lots of wonderful paradoxes or experiments in physics where things look like particles and waves, and trying to decide, is something precisely out of location. Sometimes you talk about when you apply the position operator, it collapses the state of the object down to a specific location. But then, of course, you would lose information about how it's traveling. So if you think of the probability distribution as just being, nice, then if we apply P, that should basically give us almost like a weighted average of where it is. And that's what the expected value that we're going to compute. So this over here is the commutator of P and Q. And so we're saying that these operators do not commute. It's equal to minus I times the identity. So for instance, let's just apply them. So let's apply PQ minus QP acting on some function f of x. So this is going to be P of Q of f minus Q of P of f, right? What is Q of f? That's going to just be x times f of x, right? And what is P of f going to be? 1 over I times f prime of x. Right? Now P is 1 over I times the derivative. So I get 1 over I, and then how do I take the derivative of x f of x? What do I do? Yeah, product. Every now and then it's nice to actually use something from way back when. Yeah, just the product rule. So I take the derivative of x is 1, so I get f of x plus x times f prime of x minus, now q, it means just multiply by x. So I have a 1 over I, and I get x f prime of x. Oh, okay, good. I see the x f prime of x term cancels, and I'm left with 1 over I f of x, which is 1 over I capital I of f of x. Where capital I is just the identity. But 1 over I is the same as minus I. Right? And so we see that PQ minus QP does not commute. So the next is we want to start calculating the Fourier transforms of various quantities. So the Fourier transform of P acting on F. So P is the derivative. And then we've seen that the Fourier transform of the derivative is basically the same as multiplication. But wait a minute, didn't we have a factor of I before? The Fourier transform of the derivative involved in I. Why don't we have an I anymore? Nope, there's no magnitude here. It's 1 over I. That's why P was defined as 1 over I. The constant doesn't really matter, but because I have a 1 over I, then when you take the Fourier transform, it's I times, and the I's cancel. So again, it's just chasing the constants. Okay, so the Fourier transform of PF is going to just be C F hat of C. And so the two quantities we really want to study is the position operator minus the expected value, okay? And then the momentum operator minus its expected value. And so in each one of these, we're going to just try to calculate what can you say about. So the first one is going to be essentially the variance in X space, in position space, and the second one is going to be the variance in C space or momentum space. The first one involves F, modulus of F squared as your probability distribution. The second one involves the modulus of F hat squared as your probability distribution. Okay. And so we want to see what these quantities are. And so it's just chasing through a bunch of inequalities. So we start off with 1 is equal to the magnitude of F. Well, the magnitude of F squared doesn't really matter. And then we see that this is the same as I PQF minus QPF. So why is that the case? So here, this, we'll call this 1. So 1 uses the fact that PQ minus QP equals minus II, or if I multiply both sides by I get I times PQ minus QP equals the identity. And this is an extremely common trick, is you find ways of writing the identity. We're essentially multiplying by 1. And so if I want to look at, the inner product of F with itself, this is just the integral of f of x bar dx minus infinity to infinity. This is the same as the integral of IF with F. And sometimes people use angular brackets, sometimes people use parentheses, doesn't really matter. Okay. So all we've done over here for the first step is we've just written the identity as little I PQ minus QP. All right, for the next step, we have a subtraction. So for the next step, we can take the subtraction, break that into 2 terms. So breaking it into 2 terms is not a problem. The more interesting one is for the second step, we now have the dot product of, say, PQF with F is equal to QF with PF. Is that we're moving one of the operators over. Okay? So if you think about what's going on with, imagine just QF is just some function G. So this is from PGF is the same as GP of F. And so if you just go through and think about what P is doing, what is P doing? P is taking a derivative. So we just have to prove that these two expressions are the same. That if we take the derivative of G and then hit that with F, the absolute value of F, which is the complex conjugate of F and integrate, that's the same as taking G and hitting it with the complex conjugate of the derivative of F. What do you think we use to prove this over here? Yes. Yeah, this is integration by parts. So again, we need to assume that everything converges so that we can do something like this. But if we have a derivative of G integrated against F, and we want to say that that's the same as G being hit with a derivative of F, well, if we integrate by parts, we're going to switch which one has the derivative. And then you just need the boundary terms to be. So going to the second step is actually not a big deal. Okay. The next step, why is the next step true? So why is 3 true? So we're using AB is the complex conjugate of BA. But if you switch the order, it's the same as taking the complex conjugate. And the reason is if we do this, we have A is being hit by the complex conjugate of B. And now we would have the complex conjugate of B being hit by A. So now we would have B hit by the complex conjugate of A. So when we take the complex conjugate of that whole thing, it comes back to what we started with. So 3 is just really the statement that if I have a number and its complex conjugate, so this is then, if I have A plus IB plus the complex conjugate of A plus IB. Oh, sorry, I've got a minus here. It's going to just be 2 times the imaginary part of A plus IB. And I have, to be careful, I have an I over here that's going on. And that's why I'm getting 2 times the imaginary part. So if I just subtract like this, so this should be 2 times the real part. I'm sorry? No, if I'm subtracting, I get twice the real part. But I have an I outside. And so the I outside switches the real and the imaginary parts. Oh, wait a minute. Oh, I'm taking the complex conjugate of that. Oh, you're right. I'm sorry. You're right. You're right. Yes, let's rewind. Let's go back to that. Okay. All right. So I may be making a small little algebra mistake, but essentially something like this should be true. All right. So now we only have 1 step left. And so this will be the last. And from this, we'll have the final tally for the semester. And why is this true? Yeah, this is the Cauchy-Schwarz inequality. And so for 4, we just use the integral of, say, f of x, g of x bar is thus equal to the integral of f of x squared to the 1/2 integral of g of x modulus squared to the 1/2. And if you think about it in terms of units, you can see that this does make sense. If I multiply f by a factor of 5, it's not going to change both sides. So something like this is at least a very reasonable formula. And then this is not quite calculated what we wanted. This is calculated that the length of Q of f times the length of P of f is at least a certain amount. That's almost what we wanted, but we wanted Q minus E and we wanted P minus E half. So the last little thing you have to do is you have to just go through, and you could redo the calculation again from the beginning and put in these new operators, P minus E hat and Q minus E. Or you could start playing games with the different properties we have of translations and whatnot. All right, so this finishes the rough argument of the uncertainty principle. Now, just because we showed that it's at least 1/4, that's only the start of the story. What's the next thing you might want to ask? How big is it? Or in particular, instead of how big it is it bounded by? Well, how big is it? Could you actually attain 1/4? We have 1/4 as the lowest possibility. It's got to be at least 1/4. Is that actually attained? Or perhaps there's a better argument you could give that gives an even better argument. There's a lot of arguments in math that they're trying to find bounds on eigenvalues or bounds on zeros or whatnot, and they can often show that it's at least this amount, but we actually think it's much better. Well, if anybody has ever done oh God, Ramsey theory. So you sometimes have results that at most, 2 to the 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 2, and we conjecture it's 6. We have tremendous bounds that are just absolutely astronomical, but you believe the truth is very different from that. So the question is, what is the truth in something like this? The Gaussian is a good one to look at to at least get a feel of what's going on. It satisfies every decay property you need. So if you wanted to make these arguments rigorous for the Gaussian, you can easily do it in that case. So as long as your functions are decaying at infinity, you are fine. All right, so this is a good place to stop. Just make sure someone is recording.